Hi, this is Dr. G. Vikas Paul. In this session, we'll discuss about the flexibility matrix method in structural analysis 2, civil engineering department, civil engineering subject. So, flexibility matrix method is also known as a force method or compatibility method. So, in this method, forces are taken as unknowns, whereas in stiffness matrix method, the displacements are taken unknowns. So, flexibility of a structure is defined as displacement caused by unit force. Displacement caused by unit force. So, flexibility matrix delta is equal to 3 by 3 matrix. Suppose if it is 3 by 3 matrix, F11, F12, F13, F21, F22, F23, F31, 32, F33. The formulas for these F11, F12 are F11 means integration 0 to L m1 square by EI dx, F12 integration 0 to L m2 square by EI dx, F13 m3 square, F12 is equal to F21 is equal to m integration 0 to L m1 m2 by EI dx, F13 equal to F31 equal to integration m1 m3 by EI, F23 F32 equal to m2 m3 by EI dx. So, and these are the steps. I will explain the steps while doing the problem. So, let us see a problem on this method. Yeah, here is a problem on the continuous problem on flexibility matrix method for a continuous beam. You can see a continuous beam here A, B, C, and at D and E there are point loads. At B there is a roller, at C roller support, at A it is fixed support. The first step in flexibility matrix method is, so we need to analyze this beam. So that means we need to find the final end moments MAB, MBA, MBC, MCB. All this we need to find MBA, MBC. MCB is anyhow 0 here because there is roller support at C. So first step is to calculate the degree of static independency. So generally the formula is total number of reactions minus total number of equilibrium equations. So total number of reactions are 3 at A, at B you have 1, at C you have 1. So 5 minus 3 equilibrium equations equal to 2. But here as there is no horizontal forces, we will neglect the horizontal reaction HA from the total number of reactions. That means total number of reactions equal to 4 minus, so total number of equilibrium equations are generally 3, but as there is no horizontal forces here, we will neglect sigma of x equal to 0. So 2 equilibrium equations. So 4 minus 2 equal to 2. So neglecting axial deformation HA and neglecting sigma f x equal to 0 equilibrium equation, we will get dSi equal to 2. So it is a flexibility matrix is 2 by 2 matrix. Step 2, selecting the support B and C as redundants and removing them. So we need to, in this step we need to select n out of these 4. That means reaction at B, reaction at C, reaction at A, vertical reaction at A, moment at A, vertical reaction at A, moment at A, vertical reaction at B, vertical at C. Out of these 4 we need to select 2. So it is better if we select at B and C. Yeah, this is without sinking problem. So with sinking problem also we will see. Now selecting the support B and C as redundant and removing them. So we have selected now redundants B and C as redundants. Now removing those redundants, that means RB, RC, removing RB, RC, removing those supports, we need to draw a diagram. So you can see the diagram here. So here with loads, just with loads, at B and C we have removed the things, removed the reactions. So this diagram is known as M diagram. Now step 3, assigning the coordinates to the redundants. So these are C and B are redundants. So we are assigning the coordinates now here. So 1 first coordinate, second coordinate. Next step 4, remove all the loads and apply redundants. Apply unit loads at the redundants. That means, see here, first we need to apply unit load at first coordinate, that means at C. Removing all the loads, see in this figure, we have removed all the loads, we have applied 1 kilonewton at C. In the next figure, we have removed all the loads and applied 1 kilonewton unit load at unit force at B, second coordinate B. So this is known as M1 diagram, first coordinate, so M1, second coordinate, so M2 diagram. Then we need to draw a table which consists of the columns members, origin, limits. If EI values are given different, you will get one more column like EI. Otherwise it's not necessary. In this problem the EI values are not given, that means both are same. So no need of EI column. So member, origin, limit, capital M, capital M1, capital M2. So members, let us start from the left side. So how many members are there? CE, EB, BD, DA. So CE, EB, BD, DA. So origin, let us take the first one, first support. C here, E here, B here, D here. So limits for CE 0 to 5, 0 to 5. Limits for EB 0 to 5, for BD 0 to 5, DA 0 to 5. Next, capital M values, how to calculate the moments. Go to M diagram here. First of all, take a section between CE. See here, in M diagram means in this diagram, for CE, between CE I am taking section X from C. So to the right side of it, no force is there, so 0, moment is 0. Next, come to M1 diagram. Apply cut a section here. At this section we need this is the M1 diagram, no? Yeah, this is the M1 diagram. So here apply X, it is section which is at a distance. I have shown here, you can see here this part, EC part. So at this point it is 1 into X, so 1 into X, right side anti-clockwise plus. In the same way, M2 means go to M2 diagram here. So cut the section here, this figure I have shown here. If we cut a section, there is no force, therefore 0. Similarly, go for EB now. M means go to M diagram. EB, cut a section, I have shown the figure here. Between EB, cut a section at a distance of X from E. Now at this point we need moment, that means 12 into X minus 12 into X, right side clockwise, so minus 12 into X. Similarly, this is for M1 diagram, this one, M1. Next, this is for M2 diagram for EB. Similarly, we can calculate. See here, if you see here, it is 1 into X plus 5. X plus 5 is the perpendicular distance. Similarly, we have to do for BD and DA. I have shown clearly here. You will get the values like this. So here delta equal to F11, F12, F21, F22. The F11 formula is integration M1 square EI dx 0 to L. That means 0 to 5 M1 square. That means M1. See here, all the members we need to take separately. M1 square means M1 X square plus this one square, this value square, this value square plus this value square. 0 to 5, 0 to 5, 0 to 5, 0. Everything you need to take. This is F11 value. Next, F22. If we see F22, M2 square, that means M2. Yeah, M2. 0 square plus this square. This is anyhow 0. Now this one square. See here, this X square plus X plus 1 whole square. This value will get. In the same way, F12, F21 means M1, M2 by EI. That means M1, M2. This into this. That is first one. Now it is anyhow 0. This into this 0. Now this into this plus this into S. You can see here. So this is a flexibility matrix. In the next step, we need to calculate the redundancy using the compatibility equation. Using this compatibility equation, we will calculate the redundant. Here redundant means P1, P2. That means redundants P1, P2 means P. That means at first coordinate, what is the redundant? RC. RC and this is RB. So RC, RB we will find here. So the equation is P equal to delta inverse delta minus delta. That means here P is a redundant matrix. It is a flexibility matrix which we have already calculated, F11, F12, F21, F22. This is yielding related. If it is a settlement problem, then you will get these values. If it is without settlement problem, 0, 0 you need to take. Next, delta L is displacement. Now what is this displacement matrix? Delta L1, delta L2. So for this the formula is integration 0 to L capital M into M1 by EI. For delta L2 to L, it is capital M into M2 by EI. So from this table, from the previous table, you have the values M, M1. So you can calculate these values from that table. And you will get delta L1 as this one, delta L2 as this one. Now substitute all the values here. We know this one, this one, this one. And you will get these values. You can do in another way also, like P into delta equal to delta minus delta L. So P into delta we can do, then we can equate to these values and we can find the P1, P2 redundants. Or directly delta inverse, by doing this also we can find. So in the last step we need to find, in the next step we need to find the unknowns. Unknowns means MAB, MBA, MBC, all these we need to find. So here applying sigma Fy equal to 0, So redundance we have found here 3.43, 20. This is 3.43, this is 20. Yeah, now we need to find this moment here, 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 and here. Here anyhow it is 0. Now let us find for overall thing. First let us apply the sigma Fy equal to 0 for overall. So if we apply, we'll get Ra equal to 12.5. Then for overall beam, apply sigma moment about A equal to 0. This is MAB. This is MAB. So minus MAB plus yeah, let us, if applying this, we will get MAB equal to 31.4. But to find this value MBA and MBC, so separately we have to take. First I am taking BC separately. So if I take this, I am taking this as RB2, RB1 for AB, RB2, and RB equal to RB1 plus RB2. Okay, so first I am taking this one. This is MBC. Okay, I am taking some clockwise. Here I am applying sigma Fy equal to 0. Then I am getting RB2 plus RB2 value is this one. Some value I will get. Okay, then I will get I will apply sigma moment about B equal to 0. From here I will get MBC. So MBC I have got now this value MBC value I have got. Next I am taking AB span. So for AB span, so I am applying sigma Fy equal to 0. So RB1 means RB minus RB2, because RB equal to RB1 plus RB2, no? That's why RB1 equal to RB minus RB2. So sigma Fy equal to 0. So I will get Ra plus RB1 equal to 24, Ra equal to some value. So next, so I am applying a joint equilibrium condition at B. See, at B, moment at B equal to 0. That means MBA plus MBC should be equal to 0. So MBA plus MBC equal to 0. Already we know the value of MBC from here. From here we know value of MBC. So substitute that value directly. Then we will get MBA value. MBA value. So MBA also we have got now. MBA value. Now this already we have found here. So in this way we can find the final moments, and we can draw shear force diagram or bending moment diagram, whatever we want. Thank you.